Greetings, it's Paul with a script designed to show you how to work in R with some of the probability distribution functions you've been learning about in lecture. Let's start with the most familiar of them, the binomial distribution. And we did this earlier with 3 coins. Let's do it with 6 coins now. So I start by creating a 2-component vector whose 2 elements are H for head, T for tail, and I will now make a data frame using expand grid, only this time you see I said coin 1 equals HT, coin 2 equals HT. That means that coin 1, coin 2, etc. will be the names for the various rows, and so I can get the first column by taking C6 $coin 1. That's the row, the column that alternates H and T. If I want to compute the number of heads, I create from each column a new vector that equals 1 in positions where there's an H, 0 where there's a T, and add them all up. And I can now make a table which counts the number of times each value appears. So the values are 1 through 6, and there are 23s, 15 4s, and so on in this column. If I divide by the length of the n heads column, I convert this to a vector of probabilities, and then I can use bar plot to plot it. So there's a plot of the mass function for the binomial distribution with 6 coins. But R provides a much easier way to do this. Take binom, put a d in front of it, and you get the density function for the binomial distribution. The easiest way for me to show you that this is the same is to bind together this with the previous bar plot. So I use rbind. That's R for row bind, but it's the one that works. I bind together the vector of probabilities, the vector d binom operating on the values 1 through 6. I say I want to display these side by side in red and blue, and there you have it. Anytime you want to show that 2 discrete distributions are identical, this trick will work. Now we've got the mass function, but sometimes we want the distribution function. Suppose, for example, we want to know the probability that we get 4 or fewer heads. We can do this ourselves by asking for the mean of the vector C6 $n heads less than or equal to 4. That will create a 1 in every position where the number of heads is less than or equal to 4, and the mean of that indicator function is the probability we want. It's 0.89. If we want to get all our values, we can write a function, but it's a little bit tricky. This is a function of x. It's the mean of C6 $n heads is less than or equal to x, but I discovered experimentally I have to put a vectorize in front of it in order to make sure that it works when we feed it a vector. It would work fine for 4 and get the same result without vectorize, but the benefit of vectorize is that I can ask it to act on the vector 0 through 6 and produce a vector of function values. That's the same as the built-in function p binom. So now you're getting the naming convention. D gives you the mass function, P gives you the distribution function. Now let's try computing the expected number of heads in several ways. The official way is multiply together each possible value, 0 through 6, by the mass function for that probability, sum over the probable values, and we get 3. Alternatively, we can use the law of the unconscious statistician and sum over the sample space. The sample space is just the complete data frame, and mean will average over all the rows, and that's another way to get 3. Or we can use the Tail Sum Theorem. Remember, the Tail Sum Theorem says if you have a discrete random variable that takes only positive integer values, all you have to do is sum up the probability for exceeding 0, the probability for exceeding 1, and so on. Since my.pbinom is the probability for being less than or equal to a certain value, I have to subtract that from 1 before I sum, and I get 3. If I want to do that with the built-in pbinom function, there's an easier way to do it. Pbinom 4, 6, 0.5 says, what's the probability of getting less than or equal to 4 heads when you flip 6 coins with the probability 0.5 for a head? If I put lower dot tail equals false, then instead of getting the probability for less than or equal to 4, I get the probability for greater than 4. You can see the number I just generated was 1 minus the number above. And so I can use the tail sum theorem by saying I'm just going to sum up the values of the distribution function with lower dot tail equals false. And again, I get 3. Okay, let's try computing variance. We happen to know that the expectation is 3, so we can use the definition directly. Take a vector 0 through 6, subtract 3 from it, square it, multiply by the probability of that value, and we get the variance 1.5. Alternatively, we can get the same result by taking the sum of the square minus the sum of the squared value times the probability and subtracting from that the square of the mean. That's another way of getting 1.5. Or I can do the unconscious statistician thing and sum over the sample space and just say for each row I want to take the number of heads in the n heads column, subtract 3, square the result. The mean of that result is 3. Now let's think about sampling from this distribution, simulating a flip of 6 coins. If I call the sample function with a second argument of 1, I get 1 sample. In this case, the sample turned out to have the value of 4. Call it again. Well, what do you know? I got 4 again. Ha! But on the third try, I got a different sample, 1. So these are actually independent samples, all from the same distribution. If I ask for 4 of them, I get repeated values, but these are all guaranteed to have come from different rows. The reason I got a repeated 3 is that there are many rows that have a 3. If I want to use the same row multiple times, I say replace equals true. Suppose I want to sample 100 times from this. Ooh, I got an error. What's the problem? Well, I didn't say replace equals true, and after selecting a new row 64 different times, it finally said, sorry, I haven't got any new rows to give you. So if you want to generate a large number of samples, you use replace equals true. Now I've got 100 samples, and I can make a plot. This plot should look kind of like the probability distribution, and I can check that by binding together the probabilities with the fraction of the time each value turned up. And I got pretty good agreement. There are some significant discrepancies here. Notice with 100 samples, you're not going to get that good a match between a bar plot of the mass function and a plot of the samples. However, if you go to 10,000 samples, easily done in R, now the agreement is much better. What will we do with an unfair coin? Well, if the probability of heads is 2/3, we just start with a vector with 2 h's and a t, do exactly the same thing, make a table, convert it to a vector of probabilities, and plot it. And now, because the probability of a head is 2/3, this table and the bar plot are skewed to the right. But this is a binomial distribution, and R has a built-in function for it again. I just say, give me the mass function for the binomial distribution, 6 trials, each with a probability of 2/3. And that agrees perfectly with my simulation. Topic 2. In the lecture notes is an algorithm for constructing a sigma field if you're given a certain set of events that are required to be in the sigma field and want the smallest sigma field that has those events in it. It took me a lot of experimentation to get a reasonable looking simulation here, and it's partly for that reason I'm defining n to be the size of the sample space, L min to be the shortest vector, L max to be the longest vector. Then, if I want to change these to get a more interesting looking simulation, I only have to make the change in one place. And in this case, I'm actually following good coding style. It's a general principle of software engineering. If you're using a number in a program, assign it to a variable just once, and then if you decide you want to use a different number, you only have to make the change in one place. So let's generate one of the subsets that's going to have to be in the sample space. First, I get a sample of 1 from a vector that ranges from L min to L max. In this case, it chose 6. And then I sample 6 different samples from my sample space of 10. Okay, now we know I can do it once. Now I'll do it 4 times, and I'm going to store these in a list. I'm going to make a nice list of vectors. So I create the empty list, and then running from the values from 1 through m, I do exactly what I did before. And this is my standard operating procedure in R. If I'm going to do something multiple times, I try it once to make sure it works, and then I copy that code into my for loop. And let's look at what we've got. Well, we've got a bunch of sets, one size 4, a couple of size 6s. Now let's use the algorithm that I presented in the lecture notes. We're going to have to save these equivalence classes. Let's put them in an empty vector, a list of length capital N, one for each value in the sample space. And here's the algorithm that was described in the lecture notes. We run through all the possible values, 1 through 10. We initialize the equivalence class with a vector that's the entire sample space. And then what we do is run through each value. That's going to be k in 1 through n. If it's in the set, I form the intersection with the set. Otherwise, I remove it from the set, and it turns out setDiff does a very nice job of removing set I from my class. What's left when I've gone through all the values of I from 1 through m, all the vectors that have to be in this sigma field, is I'm left with the equivalence class for k. Notice if I want to select an element of a list in R, I have to use double square brackets. So let's look at what we got. Well, what we got was most of the time there were no faithful companions of the number, but 6 and 9 always occurred together. And if you look at the sets, you'll see indeed whenever 6 shows up, 9 also shows up, and vice versa. But none of the other numbers appear reliably with the same companion. As you see, any two of these classes are either equal or disjoint. They have nothing in common or they're exactly the same. Well, let's switch to yet a different topic, the Poisson distribution. I want the Poisson distribution with a parameter 5. I'll call that parameter lambda. And I really shouldn't do this. Let's do the assignment the more orthodox way. The Poisson distribution is the limit of a binomial distribution. So I'm going to start by plotting the probabilities for a binomial distribution with 100 trials, each with a 5% chance of success. I can get exactly the same expectation if I use 1,000 trials, but cut the probability of success down to 0.005. And that looks so similar that I can't really tell the difference from what was above. Now let's go to the limit. The limit is a Poisson distribution where the parameter is 5. And if we look at all three of these together, you can see that red, blue, and green are fairly close together. This is fairly strong evidence that we are correct in saying the limit of a binomial distribution where the expected number of successes is 5 is just the Poisson distribution with parameter 5. Now, the best known feature of the Poisson distribution is that both the expectation and the variance are equal to the parameter. If I ask R to do an infinite sum, it refuses, so let's just ask it to do the sum over values from 0 through 20, generate the mass distribution for the Poisson, the mass function for the Poisson distribution, multiply that probability by 20, add it up, and I got something that was very, very close to 5. To get the variance, I take the probability times the square of the value and then subtract off from that the square of the mean. And again, I get a value close to 5. If I want to get exactly 5, I just run the sum all the way up to 50. And now it's 5 to as many decimal places as R likes to display. The same is true for the variance. However, if I put in INF, which works when you're doing integrals in R objects. It says, I started out by trying to create a vector that went 0, 1, 2, up through infinity, and that vector would be too long. Now let's look quickly at the geometric distribution. We're carrying out a sequence of trials where the probability of success on each is 0.2, and if I call the function dgeom, geom for geometric, what I get is the number of failures. It doesn't count the final success. You can see there's a value for 0 there. That means 0 failures. In lecture, I was talking about the geometric distribution, but the random variable I talked about included the final success and would have a value 1 greater. I can compute the expectation. And I get 4, and you say, hey, I thought the expectation of a geometric random variable was 1 over the probability. 1 over 0.2 is 5. The problem is that that counts the final success, R does not. I can also use the Tail Sum Theorem. All I do is use pgeom, which is the distribution function, with lower dot tail equals false. And I get a nice bar plot of that. And when I sum, again, I get 4, the expected number of failures. If you require more than 1 success, the distribution is called negative binomial. So again, the probability of success on a single trial is p, and if I want only one success, I say 0 to 20, size equals 1, I want one success, 0.2 is my probability. You've seen that before. That's the same as the geometric distribution. So let's do something a little bit different and require 3 successes. That means size equals 3. And now you can see the probability of getting 3 successes immediately, no failures, is fairly small. It goes up, then goes back down. And if I sum up to 100, I get the expectation. The simple way of getting this expectation is to say I'm going to get, on the average, 4 failures before each success. Since I'm looking for 3 successes, I'm going to get, on the average, 4 times 3 failures before those 3 successes. Now let me finish by showing you what happens in a case where the expectation doesn't exist. This can happen if you have an unbounded random variable, because you might get an infinite series that diverges. If you start with an urn that has 1 white ball and 1 black ball in it, draw a ball from it, and if you don't draw the white ball, add another black ball, you create a situation where the expectation of the number of trials before you draw the white ball is infinite. And in fact, the probability is 1 over x times x plus 1 of drawing the white ball on the x draw. I can compute the value of this function for success on the second try. Probability is 1/6, and this function is automatically vectorized. Generally, when you define a function in R by a simple formula like this, it turns out to be a vectorized function. Well, I can sum this from 1 to 1,000 and see what I get, and I get a probability that is 0.999 and change. If I push this upper limit higher and higher, I get closer and closer to 1. So the infinite series that involves summing the individual probabilities is convergent. But if I multiply by the value of the random variable in an attempt to compute the expectation, if I do this up to 1,000, I get 6.48. If I do this up to 2,000, I get 7.178. And if I keep pushing this number higher and higher, the result will just keep getting bigger and bigger. The limit doesn't exist. This random variable does not have an expectation. Things are even worse with the variance. If I square the value before multiplying by the probability, then I get a much larger value for 2,000 than for 1,000. Now let's see what happens if we sample from this population. I don't have a built-in function for this, so I defined my own. I said, let's start with the number of black balls equal to 1, and in a loop that goes on forever until I break out with return, I say, if I draw something that is less than 1 over 1 plus the number of black balls, that's the probability of getting the white ball because there are black plus 1 total balls, then I've succeeded, and this function will return black, the number of failures before that success. Otherwise, it will add another black ball to the urn. I can test this by drawing 100 samples and storing them in a vector. And when you look at this histogram, you see something kind of strange. Very high probability of getting a small value, but a few values way out on this tail. And the effect of that is that if I take the mean of this sample, I get a surprisingly large number, 3.91. Ordinarily, if you're sampling from a reasonable distribution, one that has a finite variance, and you average 100 samples, the mean of those samples of 100 is going to cluster together in a band whose width is roughly the square root of the variance, roughly the standard deviation. But here, the population variance is infinite. So let's try doing this 200 times. 200 times, we'll average together 100 samples. We'll store the result in a vector, and let's look at what we've got. Even though we're averaging 100 values together, we occasionally get very large samples, and we got one case where the mean was greater than 2,000. If you look at the actual vector, you'll see there are a lot of small numbers in this table, but there are also some big ones. We have two data sets in the course, one for delays of flights out of LaGuardia Airport and one for concentrations of arsenic in well water in Bangladesh, that show the same sort of feature when you look at a histogram or where you look at a histogram of sample means. There's no way in the real world of showing that the population actually has an infinite variance. But whenever you get samples that have occasional very large values, you should consider the possibility that a model that includes a finite variance might not be the appropriate one. Okay, it's going to tell me this is dangerously large to upload to YouTube, but I'm going to give it a try anyway.